Welcome, everyone. Thanks for coming. My name is Sid Goyal. I'm a faculty here in physics. All right. I hope I don't have to start again. But we do work in biophysics here, and I'm delighted to introduce Andrew Rutenberg from Dalhousie. He's the A.C. Fowles Professor of Theoretical Physics there for the last 25 years or so. He started as an undergraduate here at U of T. I don't know when. And then went to Princeton for his PhD, work on hard condensed matter. Hard as in not hard, but hard condensed matter. Now it's called quantum condensed matter, I'm told. Then he did his postdoc in England, in Manchester and Oxford, then a couple of years in McGill, and then started in Dalhousie. And he has been working on problems in biology when he started in Dalhousie, starting from bacteria to soft matter, and now on aging for the last 10 or so years. Welcome.
Thank you, Sid. And thank you to all of you to come here. So I'm in the physics tradition. If you want to shout out a quick question, I can address it during the talk. And otherwise, make sure you save the questions so that you ask them eventually. Now, where am I in the keynote? So this is work done largely through graduate students working with me, Glenn Pridham, Spencer Farrell, who's right here, and Amir Palvarian, and in collaboration with gerontologist Ken Rockwood, nephrologist Karthik Tenankor, and some other collaborators as well, and the funding is through NSERC. So I'm going to start my system. So I'll start with a land acknowledgement. So first of all, Dalhousie's in Nova Scotia. That's the Mi'kma'ki, which is unceded territory of the Mi'kmaq. And there's a treaty of peace and friendship for 300 years, largely neglected. And so whenever I do a land acknowledgement, I donate to Indigenous education or other charities which are appropriate, for instance, Inspire. So I was surprised a few years ago that the post-secondary funding is pretty crappy. It's not well organized at the federal or provincial level. So this is one way of compensating for that. Okay. So I'm going to start with the whole talk is going to be idiosyncratic. So it's largely based on the work that we've done on aging at Dalhousie. But I'm going to start with a bit of an intro. And the idea is that at the end, you should think physicists can do something about aging. And the other is maybe you think I'm the physicist who should be doing something about aging, which is great. Or maybe you think Andrew's doing a great job on aging, and that's good too. So it's, as long as you have an opinion, I think we're well set. Well, I was surprised, sort of thinking about a broader picture about aging, that basically healthcare dominates the provincial budget. And when you look at that breakdown, the important thing is that this is the spending per person, male and female, across different age range. And basically the cost per person balloons when people hit 65 and up. So a lot of that healthcare budget, which, I have colleagues who don't have family doctors, you probably know friends or family who don't either. And that's the issue. Now, related to that issue is a demographic transition. In 1983, when with Michael Luke, I started here at U of T, the demographics was like this, and there was a little bulge that we were at the tail end of called the baby boom, and that has propagated forward to up around here. But you see that it wasn't just a one of, it's really squared out the distribution. So people are living longer and driving more older people, which are ballooning healthcare costs and causing a lot of crisis. So the government, provincial government, federal government, us when we read the newspaper, are interested in aging as a social problem. This is demographic aging. We also know about individual aging. So I think on this sort of picture, I should be over here. And anecdotally, I remember each of these pictures being taken. This is a King's College quad in England with the chapel behind. This is the Serdans near Wallace House. And this is, actually, I don't remember this one being taken. So one of the interesting things about individual aging is even if I didn't order these in terms of date, you'd be able to order it. And in fact, if you were with maybe a little bit of practice, you could probably also guess people's ages by a year. So in your head, guess everyone's ages in the picture, have an estimation. Okay. So I was 3 then, 17 when I started university. My dad, you can see a little bit of family resemblance, was 40 at the time. My daughter's 1. I'm my dad's age. So you can see a continuity in my age. You probably were within a few years of the age guesses. You probably weren't guessing the 40-year-old was a 50-year-old or the 1-year-old was a 10-year-old, for instance. So we have this clear developmental cycle in early life. We have this clear trend. You can tell the difference between a 17-year-old and a 40-year-old, and you can tell the difference between a late 50-year-old and a 40-year-old pretty easily, whether they're dressed in a suit or not. Okay, so we have a lot of intuition, just like we have an intuition about throwing a ball in the air, it will come back down. And it's a semi-quantitative intuition as well. Okay, so you can make more quantitative when you have more measurements, not just anecdotally on the picture. So 200 years ago, Gompertz quantified mortality rates. So the hazard is the probability of dying in a year, and this is versus age, and this is a semi-log plot. So that's a log scale against age. And you notice there's a characteristic straight line, and that's called Gompertz's law. And that says that the chance of dying after you hit about 20, it's a little bump which isn't well explained. But basically there's this nice exponential increase, and there's not a lot of data past about 100, but basically when you hit 100, you're flipping a coin every year whether you're gonna survive, 50-50. And so that's why one reason why you don't see many people who are 120, but you might see, you might have met someone who's 100 in your life, but you've probably never met someone who's 120. Okay, so I'll call that aging 1.0, because if you call aging an exponential law, there's a lot of ways of recovering an exponential. So there were lots of stories over 200 years explaining Gompertz's law. And basically, it's hard to falsify any of them because they all get this nice exponential behavior. So aging 2.0 sort of extends, as I see it, aging 2.0 extends that to include health. The reason people die more often as they get older is they become less healthy, and this is a way of quantifying that. So it's looking at a 5-year period. So if everyone survives in the cohort for 5 years, they live 1,800 days. And the healthy ones, when they're younger, basically all survive. So if I took almost everyone in the room and said in 5 years, so all the people say under 50 or something like that, almost all of you will be alive in 5 years. And so your expected lifespan would be 1,800. And between healthy and unhealthy, there's not a lot of range. As you get older, there's a lot more range. And at 95, there's a huge difference between healthy and unhealthy. You still see some age effects. Even the healthiest people still start to die when they get old, but you see very strong health effects. So both health and age are coming into it. And so you can imagine you can build a model, and I'll build a model for you, which couples health and age in a process to explain this sort of stuff. This data is clean because it was from a national hoovering up data from electronic health records in the UK. So you can imagine there's 100 million people tracked through their health data. and extracted health measures. You get very good statistics. Okay. And the quantitative measure that distinguishes between healthy and frail is called the frailty index. And it's a very simple measure, which is you count up how many things can go wrong with someone, n, say 30 different things that you might measure, and you average out the number that are wrong. So frailty of 1 is everything possible is wrong, and a frailty of 0 is nothing's wrong, right? And clearly it depends a little bit on what you ask. If you include gray hair as something, that's wrong, it will have a different meaning than has someone had a heart attack before. And so there's some reporting issues, but it's an easy and robust measure. And I just mentioned, the people I collaborate with at Dalhousie developed this frailty index, and it was sort of a revolution in 2001. But it's an example of how you can make quantitative measures out of available health data. And you'll see this plot, it's roughly an exponential increase with age. Okay, so aging 3.0 is more recent, and I'd call it multi-dimensional health. And there's a lot of multis, so it's sort of multi-dimensional health. So one multi is multi-scale. So I can look at my health at a functional level. Can I climb the stairs? And I can look at my health at a tissue level. Is my kidney good? I can look at it at a cellular level. How many senescent cells do I have? I can look at it at a molecular level. How many mutations are there in my genome, or what's some epigenetic markings. There's a nice review paper I was involved with a couple of years ago where it was talking about this multi-scale issue and how do you incorporate that multi-scale data in a picture of aging. But within each of those scales, there's a lot of things you can measure. So a lot of people measure aging at the cellular scale because it's convenient. You can get cells on a Petri dish. You can extract that from someone's body, or you can grow them on your own, and you can measure anything that a biologist can measure. So there's a lot of hallmarks or cellular signatures of aging cells, many of them that you can measure. And at a functional level, people actually measure activities of daily living, like difficulty of getting up off a chair, which sometimes I feel like I have that difficulty. Some days it's hard to wake up. Some days it's hard to get dressed. But some people, as you get older, it's, most days are like that. So you can average these things and get a functional frailty index, for instance. But the important thing is they aren't all connected. You might have a cognitive deficit, which is very different from a balance deficit, which is very different from some other deficit. You might have one or the other or both, and the same with the cellular. Okay. So I just want to return to a question you might have, and I don't want to bait and switch. I'm going to do the physics of aging. I'm not going to solve aging. I'm not intending to solve aging. And so far, if I had to put my personal bet on it, this is what you need to do to live longer. You need to exercise regularly. You need to socialize regularly. You need to moderate or stop your smoking or drinking. You need to go to the doctor when you get sick and get treated. And, ideally, other things you can imagine, eat healthy, lots of vegetables, things like that. And that's it. You could invest $1 billion in some startup, and that's actually the geroscience hypothesis. So the geroscience hypothesis, which is driving the field that I'm in, not necessarily driving me, is that we can treat, is this out on YouTube? That I believe very strongly, because it's a key element of the grant funding I get. The geroscience hypothesis is that we can treat, i.e. reverse or slow aging, right? We can find the control knob, we can rewind it, and I can be 20 again. It's like out of a movie, right? So how do you operationalize that? Well, you put $1 billion into a startup tech company. If you're, for instance, Google or Meta, or you get some startup people, so Altos, Calico in silico medicine, big pharma are trying to, you know, drug this. So for instance, senolytic drugs. So a current trend is senescent cells. So you make drugs that kill them. And so the question which is begged by all this is, how do you know if it works? And the answer is, well, you have to come up with a biomarker of aging so that you treat aging, you succeed in the Holy Grail, and you rewind aging, and you can see it in the short term. You don't have to wait 50 years to see whether you die younger or older. You can do it now because you can see this biomarker rewind. Okay, so that biomarker becomes quite important, and it's begging the question of, what is this thing that we're rewinding? Right? If you imagine no one's getting older, you know, what is aging the biomarker? You know, and so the question I'm interested in more is, what is aging? And as a physicist, can we get any quantitative teeth into this question of what aging is? Okay, so this is the physics of aging, or that's aging as a subfield of physics, which is how I think of it is. But it's also called gerophysics, which is physics as a subfield of geroscience, which is maybe properly what it is. So as I see it, as I position the physics of aging, the three questions are, what are the dynamics of aging? So the Newton's laws of aging. If you can get a dynamical equation, you know how to predict things if you parameterize it and place people in it. To have dynamics, you need to have variables, and you can choose what good variables are to put into those dynamics. And importantly, to complicate things, but within a quantitative context, you can say, what are the interactions of aging, right? So Sid and I can have a social interaction. We're clearly interacting, but if I push on his shoulder, you can measure the interaction. There's a force, there's a response, we can quantify the interaction. So you need a quantitative measure, and a dynamics with parameters that you can measure is an appropriate landscape to then characterize the interactions, and you can imagine intervening in the system, just like you can intervene on Sid's shoulder once you know the appropriate force to apply. I'm going to come back to Sid's shoulder eventually. I hope it doesn't hurt too much. We're going to see if Sid dies as a result of me. Yeah, you'll see what I mean. Sorry, Sid. I didn't even ask for his permission. It's very... Okay, so I told you about frailty. It's a health measure, and I said I wanted to do dynamics, and I said we wanted to pick a measure, but we already have a measure, which is frailty. I already introduced. So let's do the easy problem and get a dynamical equation for frailty. And I already told you that it approximately grows exponentially with age. So we have an easy phenomenological law, which is exponential growth, which is fine. And we actually used that phenomenological law before we thought about it a little bit more, because there's a fundamental problem with that fundamental law, which is that exponential growth goes to infinity. And frailty is a percent of things wrong, which can't be bigger than 1. And so you know that law, as attractively simple as it is, and as appealingly tractable for doing calculus and being a physicist, it has to be wrong. So then you think about what's a better way of doing it, and a better way of doing it is more of a master equation. So I'm just writing this as a deterministic equation, but we do a proper stochastic implementation. The rate of change of frailty is given by damage, which increases frailty, and repair, which decreases frailty. The damage is only happening to the undamaged fraction, and the repair is only happening to the damaged fraction. And you can see that as f approaches 1, you can't damage anymore, and it has a natural mathematical limit. It can't exceed 1, and it can't go below 0. So it's appealing. And so we modeled this, and we modeled it with a standard model. And I should call out to Spencer, who got us started, and Glenn, who implemented this particular model. So we implement a standard assumption in the field called proportional hazards, which is that the risk, for instance, of damage, the age dependence is exponential, and it's a factor which multiplies, for instance, the health dependence or some basal rate. It's called proportional hazards. It's tractable, so we allow for age and or health effects in damage and repair. We find with an analysis of available data that damage increases with increasing age and increases with worsening health, increasing F, frailty. And in contrast, repair decreases, so maybe we could have put minuses, but the coefficients, the model parameters are negative for the age dependence and the health dependence in the repair. And then we can also put in a mortality term, which has a similar behavior, which increases with age and frailty as well. Okay, so we have available data. So I should say that aging 3.0, this multidimensional health, one of the reasons it's now on the picture is that most countries have one or two large what are called longitudinal studies of aging. So there's a Canadian longitudinal study of aging, English longitudinal study of aging. There's a health and retirement survey in the States. And one reason they have about 10,000 people enrolled, they measure them every 3 years, and it's a few $1 million every time they measure them because they have to drive out and survey them and take blood and keep track of the data and things like that. So it's a national effort, but there's a lot of these data sets which have emerged, and you can do this sort of analysis, construct health, and look at how people's health evolve. And we use those then to constrain these models. Okay, so what do we find? So this is data on the left from American Health and Retirement Survey, and on the right, well, we'll see. Yeah, on the right, ELSA, English Longitudinal Study of Aging. And the plotting, the vertical axis is frailty. So unlike I made a graph for public, which was prettier, and I put the health on the top and the poor health on the bottom. Here, the health is on the bottom and the poor health is on the top. That's the original way we did it against age. And what you see is the red line is the NULC line. So maybe I'll go over here. The red line is the NULC line. If you're, in a sense, it's the stable line. And so if you're above, if you have poor health and you're young, you tend to drift down towards good health. And if you have good health and you're older, you tend to drift up towards poor health. Okay. Qualitatively, this is about right? When you're young, whatever happens, you're usually fine after a few months. And when you're old, the opposite happens. And what's interesting from the data is you have this very sharp transition at about age 70. What I've put in as well in the dashed line is you can see some contours in the background. The dashed line is about as old as unhealthy as the population gets. The dashed lines vary a little bit from study to study because of the questions asked and the population enrolled. And you can't think about a person being tracked through because people enroll and drop out of the study, and they tend to balance the demographics. But you can get a sense from the contours where the data is well sampled. So we don't actually know what's going on up here because there's no people who are that sick at that age. Okay. But that dashed line is roughly speaking where mortality runs in. So what you find is that when people, if you imagine a stable, very poor health at old age, people never get there. If you imagine someone with 70% of all possible chronic diseases, they don't survive that many years. Okay. So importantly, if you look at a certain age, there's differences in this. The arrows indicate the rate of change of frailty with age. That changes, and at a given frailty, it changes. So both age and frailty affect things. And that NULC line, we have a mathematical form for it because we have a mathematical model. And in particular, you can set 0 to the derivative of frailty. You can solve the algebra, and you can see that certainly it's a ratio of the repair and damage that's coming into the equation for that null cline. Okay. So following that null cline math, if it's a ratio of those two things and those two things are exponentials, then it's actually the differences of those parameters that are coming into the null cline. And you can believe or do very fast algebra that you can get an equation like this. And in particular, if you solve for age, it's coming in one place. If you solve for frailty, it's coming in two places. And so if you solve for age, there's two terms with frailty. Those delta parameters control it. There's some weird complicated logarithm. And so you plot it out. And you can see that one delta parameter, delta t, controls the scale of time. Delta 0 controls an offset in time. And delta f controls a slope, which controls the shape of a sigmoid. So you're sigmoidally going that null cline had a sigmoidal shape, and this delta f controls the shape. And our best estimate of that is, as a point estimate, is vertical. Okay. So we can go from the data to this picture, and we can get some interesting results. So one thing is damage propagation. This is the idea that you get sick, you're more likely to get more sick. And we find damage propagation in our model, which is to say, if you decrease in health, your rate of decreasing in health gets bigger. And that is observed after that singular transition, after age 76. Eventually you saturate, because of course you can't keep getting worse past 1, but mortality effects basically come in to screen that saturation at high frailty, so you don't see it. So you see a little bit of this damage propagation, which people report in the field, which is recovered in the model. Okay. So here's the summary. This is the picture that you saw before. Below age 75, good health is stable. Above age 75, damage propagates. If you get too sick, you tend to die. And there's a sharp transition separating that. Okay. And interestingly, and hopefully reassuringly to people who are 75, you don't follow the null cline. The null cline is just where you don't tend to move away from. So if you're healthy, you tend to stay healthy. It's just that once you start getting sick, it's harder to recover from that process when you get older than when you're younger. When you're younger, if you start getting sick, you tend to come back to the stable line. Yeah, so the wisdom for older people is stay healthy. If you get sick, take care of yourself. Yeah. Okay, in a sense, no surprise, but we're seeing it. Okay, so when do I keep going till? 5 till. Okay, I just have to make sure I'm gonna do this middle one really quickly. Okay. So I said that so our next job is, okay, mission accomplished, go home, pat ourselves on the back. But I want to keep doing things. And so you have to go into this multidimensional health. So how do we do dynamics of multidimensional health? That was the dynamics of frailty. And we're done. We can't do anything more. So one thing is to take the elements that are coming into the frailty. So for instance, these activities of daily living or chronic diseases, and see when they occur. And the problem is that even though they're 0 and 1, that they're complex emergent processes. It's not like someone turns blue when they get dementia or when they have a heart attack. Nothing's wrong, and then suddenly it goes to 1. So people like Uriel Long, who I guess he says systems medicine, but let's say the physics of medicine, say, okay, let's look at some dynamical processes, disease by disease under the hood. And it's complex. You have to be sort of smart and look at it, every disease. I'm a classic physicist, so I'm quite lazy. And so what we decided to do instead is take the latest shiny tool and take the data that we have available, shove it into a universal learner, so a deep neural network, and predict risks for transitions of these diseases. And then you say, well, maybe we'll get lucky and we'll get something sensible, and maybe we won't. We got something sensible. And the thing that you can tell sensible is actually, how do you know if you get the risk right? Because the person either got the disease or didn't. How do you know it was right? And the answer is you use your estimate to group them in risk. So I say, I think I know everyone's risk for getting diabetes in 5 years. So I'll take all the high-risk people together and all the low-risk people together, and then I'll look at the prevalence of actually the diabetes emerging in the high risk and low risk. And if I predicted 80% and 80% of them get diabetes, and I predicted 10% and 10%, then I say it's a good prediction. Those risks were real. It was well calibrated. And we find in the blue points, we have very well calibrated model right along the diagonal between predicted and observed, predicted on the X and observed in the Y. For low risks, we don't. Okay, and one reason for low risk we don't is for low risk, we don't actually see it happening. And so reasonably enough, we wouldn't be able to predict it well. Okay. Interestingly, and this is work still yet to be published, but submitted anyways, is that if you look at the histogram of risks, disease by disease on a log-log, we see a characteristic power law tail. So the high risk looks like it's power law distributed, which as a Pavlov conditioned theoretical physicist, I say power law, that's for physics. And so we're sort of interested in, why do all the diseases have approximately the same power law tail? What's the origin of it? And so we're quite excited about this and following it up, but we don't have the story yet. Okay. So I'm going to give you instead a story that we have much more completely, which is if I take a blood test from each of you, and then take another blood test from each of you a year later, and you could probably run your own data on these models that we have if you have access to your health record and you have a doctor, so you've actually had blood tests. So maybe they measure 30 things, and the question is, what's a quantitative model to describe all these blood tests that you take? Okay. So we should have a dynamical model. It's going to change. There should be interactions in the model. If you think that your body is actually doing things together, there should be some relationship between these different, if your blood sugar is high, it's going to affect other values. If your blood sugar is low, it's going to affect different values. We would nevertheless expect it to be homeostatic. Sid, you alive? Yeah. So not only did I hit Sid on the shoulder, but Sid had something weird for breakfast this morning, a little bit different, or for lunch, right? I certainly had a different lunch, right? I had a pizza with gluten and I'm gluten-free, right? And why did I do it? Because I'm basically homeostatically regulated. I knew I could hit myself with a few slices of pizza and it wouldn't kill me, right? I am not a house of cards, right? Where you make a little perturbation and down it goes. Okay, so we expect the model to be homeostatic, and yet we also expect it to be quite stochastic, right? If nothing else about whether you eat lunch early or late. Okay, so the picture is as simple as possible, but not simpler, which I'll ascribe to physics in general, or I could misattribute it to Einstein. And we call it a W dynamics. And again, Spencer led the way with a nice machine learning program, a machine learning approach to the same data, which showed that this is maybe the right direction to go. And then Glenn Pridham more recently took it to town. And here's the model. So Y is a vector of features in machine learning language. So Y is a vector of blood measures. N is the time point. So yn plus 1 is minus yn is how much that measure changed from one measurement to the next. W is an interaction matrix. So it allows something to, one value to change a different value. Mu is a fixed point. So if y is equal to mu, it doesn't change. And epsilon is noise. So there's a couple things in here. This is a standard physics approach, which would be to power law expand. If you don't know what to do and you don't want to use machine learning, perturb, right? And so you can read the right-hand side as a constant term plus a linear term plus noise. And the noise is a sort of a rescue bag because the noise is any misfit. Anything we've gone wrong in the model goes into the noise, right? Okay, so it's a good start anyways. And one of the first things we find, and every time we've looked at it, is that and there's a delta t, a time scale, just in case you want to make this a stochastic differential equation as opposed to a stochastic difference equation. We hide a delta t in the W. The W is age independent and health independent in the data we've looked at. So young people and old people have the same basic biology. The noise is age independent as well, at least to the extent to which the quality of data that we have. And that already says we're doing something right, because it says in this modeling picture, things are already simpler. So it's a good approach forward. So what does that leave? Well, that leaves what the W is and what the fixed point is and what the noise does. Okay. So one question you might ask is, well, you measure 30 things in the blood, but the body's complicated. How many genes do we have? 10,000? You know, they're all in the blood. You know, you pee in a jar and you can measure 10,000 things. In the blood, there should be 10,000 things. So most of the things that are in the blood, we don't actually measure when you do blood work. So what are all those things doing? Well, within the model, if you measure something, it can push on the other variables through this W matrix. So an off-diagonal term will allow one variable to push another one. So if you imagine all those unmeasured things pushing, the only thing that can push in this model is the mu. So you can imagine all those unmeasured things pushing through the mu. So we look at the mu, and when we fit the data, we find that the mu often drifts, right? And we can say, okay, depending on what all those things that are pushing, if they're drifting, they can drive the mu to drift. So things like blood pressure will drift up with age. And so this is a mechanism allowing that age dependence. And we find this linear drift is a good fit for the age-related variables. Okay. Interestingly, if you imagine, again, a stochastic differential equation and mu is drifting, and this is all, oh yeah, I have to come back to the stability. This is trying to follow that fixed point, but it's moving away from you. You're like a greyhound following the carrot at the racetrack. You're not actually catching up to it. So the drifting aspect of the fixed point means that you're not oscillating around the fixed point. You're sort of oscillating, trying to track it. And I should just say, this is the way we've written it is to emphasize the stability. So depending on the eigenvalues of W, you know, in a quantum sense, you can get stable or unstable. So we expect stability. Sid's still alive. I'm still alive, despite the pizza. It tasted good though. And so we expect stability, but weak instability would be fine. So if there is an unstable mode in my biology, but the time scale was 100 years, I wouldn't mind it necessarily too much and might not notice it. Okay, so here's the raw thing. The PowerPoint doesn't resolve it, but you can see some little things off diagonal. All the diagonal terms, this is the raw W, are stable, which is blue, negative. If you diagonalize it, so you find a rotation, a linear rotation unitary matrix, you get something which is entirely stable. We've never seen an instability. Okay, so this is consistent with the homeostasis. That thing which diagonalizes it also defines natural variables or eigenmodes, and you can rewrite the dynamics in terms of them, and they decouple from each other in terms of the dynamics, these linear dynamics. And so each one you can look at separately. We call them natural variables. And so you can distinguish them by how stable they are, how big the magnitude of lambda is, and you can look at how much they drift through this fixed point value, and also how noisy they are. Okay, so the time scales, you know, range from the life scale. We've rescaled mice up, and so we can rank order them. So some of them are, you know, 40 years, and some of them are, you know, 4 times that, 4 times faster than that in this data set. Okay, so a great range of timescales. And interestingly, if you look at people with, say, one of those not the raw biomarkers, not blood sugar, but one of these eigenmodes, think quantum mechanics, right? The natural representation. So if we pick one of these natural variables and we can measure each person for how much of that natural variable they have, and then we can see whether they died or not. So you can do a survival analysis, and this is the standard, like I said, proportional hazards term for the survival, and this beta is a coefficient, which then, if the beta is big, it means that variable is dangerous. Okay. And so you're plotting beta, in this case, against the drift rate. And this says that if you drift a lot, that variable is dangerous. So it's sort of double jeopardy. If a variable is drifting a lot, the drifting is driving the variable to a large value, and those are the dangerous variables. And it's always drifting in the hazard direction. So if it's drifting in the negative direction, the beta is negative to make it dangerous. If it's drifting in the positive direction, beta is positive to make it dangerous. There's a couple of exceptions, the red ones, but basically most of them follow that rule. If you look at the red one and you plot it differently, now you plot the hazard coefficient against how slow the variable is, you find that the slowest ones are the ones that are most dangerous. So the slow ones are dangerous, but the slow ones, when they deviate from health, they take a long time to go back. So again, double jeopardy. The slow ones are exactly the ones which are dangerous, we find from the data. So we call these different, one is allostasis, like homeostasis, but bad, and the other is stochastic accumulation. So we have two modes of damage, but the slow ones and the drifting ones are both bad in a double jeopardy way. Okay. The noise is also interpretable. So this goes into the eigen thing. You can diagonalize the W. You're not diagonalizing the noise. Technically, you talk about the noise as a covariance matrix, so how these variables correlate with each other. And so you could stab one leg, you can stab the other leg, but if I injure my legs, it's probably like a car accident. So there's a correlation, right? So even though they could be independently injured, there's a correlation. And we see that in the noise, all the extrinsic effects in the model come in this block diagonal form. And these eigenmodes are rank ordered in terms of recovery rate. So it says that somehow these blocks are dynamically coherent. The one variable and the other variable that are tied together by extrinsic effects, by noise, by injuries, by medicine, by biology, we don't know, have about the same timescale and look like they're coherently evolving. So we had three things that were left: the W, the drift, and the noise, and they all seem to have some interpretable, meaningful impact. Okay, so here's the summary, that we can simplify this multidimensional aging into something which gets this nice interpretable picture of what's left. Okay, so I said physics of aging, variables of aging. We have a summary measure of health like frailty index. We have these natural eigenmodes from the W analysis. We have disease risks. The dynamics of aging, we have this stochastic master equation driving the frailty dynamics, damage and repair of these binary deficits. We have this stochastic difference equation or differential equation for the continuous variables, very simple. We don't have a dynamics for the risks yet. And the interactions of aging, the F, we don't really have more than one thing. So the F is just coming in self-consistently in its dynamics. But the interactions of the multiple high-dimensional biomarkers are slow, simple, and age-independent. So you measure in one population, like a healthy population, and it looks like you can use that for other populations. We don't know about the risks yet. Okay, so I'm probably over 5 minutes, so I'll just say 3 questions. I talked about 2 different pictures: the frailty index, or your health, and also these biomarkers. And we think that if we measured enough biomarkers, we should have a good like 10,000 of them, 1 million of them, we should have a pretty good picture of people. And so how do we reconcile that biomarker picture with this damage and repair picture? So one way is you could start with the left. You could simulate the biomarkers. You could binarize them into health, and we have some systematic ways of doing that. And you can look if they satisfy this health dynamics. And if anything in the damage and repair picture is different, or if it works or not. We're doing each of these in the fullness of time. And on the other hand, if you have these discrete states, like someone has diabetes or not, you could include them as, you could condition the fits, you could include them as discrete forcing terms in the biomarker dynamics, and in a large enough population, figure out how they're forcing it. So those are both good ways of doing it. Maybe there's others. You can ask, well, here we have a population level, but I want to know about me. And I want to know about, if I take some blood pressure pill, am I going to live longer, right? Or how's it going to affect my health? So I need to include that exogenous effect, because the model isn't going to tell me when I get prescribed with a blood pressure pill. But if I start taking it, what effect will it have? And the same thing if I, get run over by a car while I'm cycling, or have a chronic disease or something like that. How do I include those? So the first thing I'd say is, in the population level, all these interventions are happening. We're all having health care. We're all doing things. We're going to the doctor or the hospital. But if we explicitly include them, then we should change some of these terms. So these terms will include them implicitly on average, but explicitly including them would then change those average terms and should improve individual fits. If we understand what a medication does and we know whether someone has that medication or not, we should be having a better picture of both the discrete and the continuous models. Last question I'll say is, I've talked about human health, but you can ask about health of dogs. And there's a recent, like I talked about longitudinal human data, there's a huge longitudinal dog, companion dog project, citizen science, called the Dog Aging Project. There's a large mouse study with thousands of mice doing the comparable thing with mice, which is still embargoed by a Harvard group, but it will come out. There's been studies by the US Navy on their trained dolphin population. And there's very good open science on C. elegans roundworms, which is sort of a simpler organism, and you can think of other organisms as well. So you can look at, for instance, any of the things that I've talked about, the shape of the nucleus, these power law risks, this age independence of the interactions, and you can say, are those universal? Do mice have the same behavior? What about dogs? And I put in this ordering provocatively because dogs and humans have health care, so pervasive interventions targeted for when you get acutely ill, and mice don't. In fact, oddly, if you have a mouse colony, you have to kill them when they get sick enough, as opposed to helping them. So you can have, just by looking at the model organisms, you might be able to get a sense of what cumulative, aggregate effect of healthcare is on population health, which is hard to get otherwise, because we don't have good population health data for humans for people who don't have healthcare. You sort of need a healthcare system to get the data to talk about people. You can get mortality statistics, but it's hard to get high-dimensional health data. Okay, last, you're trying to predict the behavior of human aging. Just model it as a stochastic difference equation. Add some secondary terms to account for, I don't know, drifting baseline. What do you need a journal? What do you need all these geroscience journals for? We're done, right? And I'll just remind you that there's a lot that I haven't covered. I haven't talked about genetics, haven't talked about evolution, I haven't talked about specific biological mechanisms, I haven't talked about biological effects, I haven't touched the molecular cellular level, I really haven't touched the tissue or organ level. I've glossed over the possibility of interventions, but haven't tracked them. I alluded to medical care, but haven't tracked it. I haven't touched on socioeconomic factors. The list goes on. So, you know, human aging is a big part of medical care, which is 50% of provincial budgets. It's, you know, all of CIHR and a lot that goes around the world. So there's a lot of work done on aging. It applies to every biological organism. And hopefully coming back to the beginning, I'm saying physicists have something we can contribute. The tools of physics can give us some insight and simplicity, that nice thing for physicists in this problem. So done. I have a web page. We have online seminars for biological physics. Also do work on Collagen Cafe. And as the students who met me, I have a physics of aging pencil swag if you're daring enough to come up here.